Hello everyone. In this series of 4 videos, I shall be covering reactions of halogenoalkanes for both standard and higher level IB chemistry. In this video, part 1, I will be covering or focusing on standard level reactions of halogenoalkanes. Higher level mostly requires your knowledge of the mechanisms by which these reactions occur, which will be covered in parts 2, 3, and 4 of this series. Reactions of halogenoalkanes. Reactions of halogenoalkanes. Halogenoalkanes undergo nucleophilic substitution reactions. By the name of this reaction, you can tell a lot about this reaction, that it's a substitution reaction. Substitution reactions involve one atom substituting another in another molecule. Nucleophilic, meaning the atom substituting the other, is going to be a nucleophile. So basically, to define nucleophilic substitution reactions, I would state it's a reaction in which a nucleophile substitutes a halogen in a halogenoalkane via heterolytic fission. The term heterolytic fission, or the process of heterolytic fission, fission meaning bond breaking, is a requirement for HL students only, which I will cover in this video. By now, you learned that these curly arrows, double-headed curly arrows, represent the movement of 2 electrons when drawn in reaction mechanisms. Heterolytic fission means the breaking of bonds in which the electrons shared in a covalent bonds are not evenly distributed once the bond breaks. So for example, in this example where X is the least electronegative element, imparting it with a partially positive charge, while Y is the more electronegative element, imparting it with a partially negative charge. Once the bond breaks, Y, the more electronegative element, gains both electrons in the covalent bond, forming ions. As you can see here, Y gained both the blue and the red electrons in the covalent bond, forming a negative ion, while X lost an electron, forming the positive ion. Thus, heterolytic fission is a process in which ions are formed once the bond breaks. A nucleophile, on the other hand, is a neutral or negatively charged ion that reacts by donating a pair of electrons. Thus, a requirement of a nucleophile is to have a pair of electrons which it can donate, and thus are considered as electron-rich species with high electron density. Thus, these species would be attracted to regions of low electron density that have a formally positive or partially positive charge. Examples of nucleophiles, neutral and negatively charged ions, neutral molecules and negatively charged ions, are ammonia. Ammonia is a neutral molecule that has a nitrogen has a lone pair of electrons which it can donate. A water molecule, the oxygen has 2 electron pairs and it can donate one of them. The hydroxide ion is an example of a negatively charged nucleophile. The oxygen atom has 3 lone pairs of electrons, and the cyanide ion is another example of a negatively charged nucleophile in which the carbon atom, the least electronegative atom, has a lone pair of electrons which can donate to form a covalent bond. Generally speaking of nucleophilic substitution reactions, as you can see here, when a carbon atom in a halogenoalkane is bonded to a halogen atom, the halogens normally have the higher electronegativity value, and thus the electron pair in the bond spends most of its time closer to the halogen, imparting it with a partially negative charge, while the carbon is imparted with a partially positive charge. And thus, this region is a region of low electron density that would attract or seek species with a high electron charge density, such as nucleophiles, and thus the nucleophile would donate its pair of electrons to form a covalent bond with carbon, while halogen gains both electrons in the covalent bond formed with this carbon atom to form the halide ion. Before we cover examples of nucleophilic substitution reactions, students should learn what a primary, secondary, or tertiary halogenoalkanes are. A primary halogenoalkane is a molecule in which the carbon atom bonded to the halogen group is bonded to one alkyl group only, as in one bromobutane and one chlorobutane in this example. On the other hand, the secondary halogenoalkane is a halogenoalkane in which the carbon atom bonded to the halogen group is bonded to two alkyl groups, such as 2-chlorobutane in this example. And finally, the tertiary halogenoalkanes, in which the carbon atom bonded to the halogen group is bonded to three alkyl groups, such as this example. The name of this molecule, if you locate the longest continuous chain, which is this 3 carbon atoms, and you number them, the methyl group and the chlorine atom would be on the second carbon, the longest continuous carbon chain, and thus would be called 2-chloro-2-methyl propane, named in alphabetical order. To cover examples of nucleophilic substitution, the most common example in exams would be the reaction of halogenoalkanes with NaOH, sodium hydroxide, or potassium hydroxide, KOH. Students should be able to notice that the Na and the sodium ion and the potassium ion are spectator ions, while the nucleophile in this reaction is the hydroxide ion. An example of a primary halogenoalkane would be chloroethane, in which the carbon atom, this carbon atom bonded to the chlorine group, is bonded to one alkyl group. Its reaction with the hydroxide ion produces an alcohol, which is ethanol, in which the hydroxide ion substituted the chlorine atom to form ethanol and the chloride ion. Nucleophilic substitution reactions are very important in organic synthetic routes, as many different functional groups could be added to a halogenoalkane to form different functional groups. In this case, when we add the hydroxide ion, you'd form an alcohol, while if the nucleophile was ammonia, you'd form an amine. If the nucleophile was a cyanide ion, then you would form a nitrile group. So it's a very important point in organic synthetic routes, because many different functional groups can be formed from halogenoalkanes. On the other hand, for a secondary halogenoalkane example, I used 2-bromobutane, in which the carbon atom bonded to the halogen group is bonded to two alkyl groups, the methyl and the ethyl group on this side. Thus, its reaction with the hydroxide ion would substitute the bromine atom to form butan-2-ol and the bromide ion. Another example would be a tertiary halogenoalkane, such as 2-iodo-2-methyl propane, in which the carbon atom bonded to the halogen is bonded to three alkyl groups, such as this molecule down here. The hydroxide ion would substitute the iodine ion, forming 2-methyl-propan-2-ol and the iodide ion. This mostly covers standard level requirement for reactions of halogenoalkanes for IB chemistry. In the next part, what you will notice here is that all three reactions are identical, in the sense that the nucleophile simply substitutes the halogen atom to form an alcohol in this case, and the bromide ion. A requirement of higher level students in the IB chemistry is the mechanism by which these reactions occur. The mechanisms by which these reactions occur differ depending on whether the halogenoalkane is a primary halogenoalkane, secondary halogenoalkane, or tertiary halogenoalkane. The main overall reaction occurring is the same in all these reactions, but the mechanism by which the reaction proceeds differs, which will be covered in parts 2, 3, and 4 of this series of videos. Thank you for watching.